Okay, Section 4.5, matrices for scale change. You've done scale changes in geometry. Now we're expecting you to look at them and see how you would perform a scale change using matrices. So recognize the different relationships of the figures. That would be the review part from geometry. Relate scale changes to matrices and matrices to scale changes. And then be able to graph figures and scale changes fairly quickly using some of our new notation shortcuts that we'll be showing you. So with that, let's move to, we have Mr. Giraffe. A scale change you read about, the symbol is S sub A comma B, where A is the horizontal change, left to right, and B is your vertical change. So as we change something, we know we're talking about using a positive scale only. So if that's the case, then our A value can go to the right, and our Y value can go up. So we could stretch this quite a bit. All right, using that idea, let's start talking about characteristics. If I took Mr. Giraffe here, I made a copy, and asked you to come up and scale him by some horizontal movement. So if we wanted you to scale him by some horizontal, that's on the X only. So I could say, let's make him, and start looking at that. All right? Same giraffe, and all I've done is made the X-axis 5, 6, 7 times bigger. So what has happened? If you look and compare, and take this and put it back over here, he is still the exact same height. We did not touch that. But something happened when we stretched him out along the x-axis. Okay? If we put him back or just slid him back, okay, because we can reset, and pull him out again and do the same thing, but just change the vertical, which means we're going to move him up or down. Now if you look, again, move him back because it's going to be quite obvious here. He is the same width. The picture did not change that way, but obviously he changed his height. Now some other things changed when you looked at that. And we could make one third and final change, and that would be if we came out and said, well, let's change this by moving him a little on the x-axis and a little on the y-axis. So question is, do the two shapes look the same? Images in this case. And I think most of you can say no. We've got a little distortion maybe going on. His neck in this new one doesn't look at all as long as the other. His legs look a little shorter because his neck isn't as long. So what's really going on? Those are the things we want to look at. So if it's not an image, maybe it would be just a regular shape. So let's take our triangle here. And you can see right now, and let's move it actually down here. All right, so we can see it's about 1, 2, 3, 4, 5 across and about 5 high as well. If I sit it in there just right, it's not quite right, but close enough. So he's 5 wide and 5 high. So let's take a new triangle and let's place it over here as well. But let's now make it, starting at that same corner, let's make him twice as wide. So that means, whoa. Okay. So my question to you is, what happened? What characteristics? Are those the same two triangles now? Yes, they're both triangles. But that first one was definitely equilateral. The one we have now, is it equilateral? Is it something else? It just went through a scale change on the x-axis only. If we go back and do the same thing again and bring that triangle out and move him back over here so we have a little more room, and this time made it a scale change in the other direction, which is just vertically, we could maybe say, oh, well, if I move him vertically, now look at that. I think that's a little more obvious. Do we still have two equilateral triangles? What's staying the same? What's changing? What is preserved? What is not? And then last but not least, if we take our triangle, move it in both directions. So we could move it double the size horizontally. And can I go double? I can probably go double. He still looks pretty equilateral. But are the sizes the same? No. Are the angles, are the edges? All those things have to be talked about. We could also go down to a positive movement that is, if we were at 5 and I only went to like 2.5 for my height, I doubled the x, but I made it only half as big. You can see what's happening. So what I want here is, you can tell by the list, what are the characteristics of the shape that has gone through? Make your list. Be as specific as possible. You know, what's preserved, what's not. If you think edges, something happens to the edges, write that. So write your characteristics, and you might even be able to come up with more than 4. And those characteristics we definitely will be discussing and sharing in class. So make sure you have those ready. Knowing that, if we talk about a scale change, and knowing we can move in one way or another, let's go with this. A scale change is not necessarily a similarity transformation. So we have definition for similar in geometry. Same shape, not exactly the same size. So they are similar, but they don't have to be the same size. The ratios of the corresponding sides may differ. Think about that. If that's the case, the shapes are really not similar because they're not the same shape any longer. The ratio of the edges has changed. In a scale change, if the amounts of change are the same, then the scale change is really a size change. So if I went twice the size on the x-axis and twice the size on the y-axis, then I'd have a size change of 2, 2, which means I was really changing it uniformly, and so it really is, as they said, a size change. So S sub A comma B, where A and B are equal, is really a size change. Here are our shortcuts and names that we need to go through. We already said a scale change was the S sub A comma B, because you have to take into account both scales. And so the notation for our the matrix is A, 0, 0, B. A affects the x's, B affects the y. So if you would multiply a point matrix by your A0, 0, B matrix, so we got a 2 by 2, and if I did a 2 by 2, A0, 0, B, times a point, a generic point, xy, and if you multiplied that out, first row, first column, you'd get AX. Second row, first column, you would get a BY. So the shortcut is the X values get changed by A, and the B values get changed by Y. So knowing that, let's try one. Scale change. If we say graph the polygon represented by. So right now we're going to say in red, we will graph the original. So here we go. 0, 4. 1, 2, 3, 4. 4, 0. 4, 3. And lastly, 0, 3. Oops, I definitely screwed that up. Oh, no, 0, 0. Went ahead of myself. 0, 0, 4, 0, 4, 3, and oops, I have that off. I have it as 0, 4. So let's just move that because, let's go again here. So in red, we've got 0, 0. Got to be able to count to do this. 4, 0, 4, 3, and 0, 3. So there is our new rectangle. If you wanted to connect them, you could. But we can visually see that. So now it says label it A, B, C, D. And if we did, we'd have A, then B, then C, and then D. It says perform a scale change of 5, 2. So that tells me that we got to change all the x values by 5 and the y values by 2. So now let's call our new one after we write it out in blue. And we will graph it in blue. So all the x values change by 5. Well, 0 times 5, 4 times 5, 4 times 5 again, and 0 times 5. Then 2. 2 times 0, 2 times 0, 2 times 3, and 2 times 3. So now, let's see if we got enough here. 5, 10, 15, 20. Ooh, just close enough. If we go 0, 0, we're going in blue. I still have that point 0, 0. So that's on both of them. Then I have the point 20, 5, 10, 15, 20, 0. Oops, slide that over a little. 26, 1, 2, 3, 4, 5, 6, and 0, 6. So there is my new graph. You can see how much it has changed. Label it A prime, B prime, C prime, D prime. It is a new rectangle. Then perform the scale change of 2, 5 on that. So one more step here, and now we're going to take a 2, 5, and actually let's make this one green, on that original. Perform the scale change of 2, 5 and label it. Now that really doesn't say on the original, so let's assume, like in the last one, it was on the previous graph, so they were all transformations. Maybe it was on the original, but we did it on the previous one, so let's go in that same direction now. So it's a 2, 5. So a 2, 5 would change all of those by 2 on top and 5 on the bottom. And I think my graph's not big enough. I didn't count. And so we've got 0, 0 still, which would be on both. We have 40, 0, and we're already out at 5, 10, 15, 20. So 40, 0 is going to be way out there. 40, 30, you'll be way up there. And 5, 10, 15, no, we don't have enough to even show 30, and 0, 30. So you can see that's huge. So there are your transformations, and doing the transformations with the shortcuts and then graphing. So I think all scale changes that have different A-B values will show you a different size combination, and all scale changes that have the same XY values will show you what we would refer to as a size change. So with that, you should be able to see similarities. Again, memorize and add those notes and shortcuts to your list. Our list should be growing now. Remember, we're going to have about 10 of them by the time we finish. So that's all for now.